All right, sigma and pi bonds are actually a pretty quick and easy, again, column to fill out. While after the first minute, you probably can just take away this lecture, stop it, and go back and fill out the columns. It's a pretty simple technique. The explanation, I want to go in a little bit deeper again, just for those of you that might understand why and what it all results in. Okay, because I still think that's an important concept as well. So a sigma bond is any single bond. All single bonds are classified as sigma bonds. They're also the only bonds that count towards the number of electron domains. Remember when we said before that if you have a central atom and it's got a double or triple bond, that still only counts for one electron domain. It doesn't count for two in a double bond, it only counts for one. And that's because of those two bonds, one is a sigma bond, the other one is a pi bond. Because in a multiple bond, one of the bonds is a sigma bond and the other is a pi. So in a double bond for carbon, that first bond might be a sigma, the other one might be a pi. And they're symbolized by the Greek symbol for sigma and also for pi. Okay, the pi symbol that you use with the mathematics. So that's pretty much it. I mean, if you had to go back to your column now on your table and fill them out, whenever you have, if they're all single bonds or sigmas, just count up how many bonds there are. If there's a double or triple bond, one of those bonds labeled as a sigma, all the other ones are pi bonds. So a triple bond, one of them is a sigma, but the other two are pi bonds. So in a triple bond, you have a sigma bond and two pi bonds that you need to account for when you add up all the bonds. So every dashed line counts for either sigma or pi. You just got to count them up and put them down on filter table work. That's all the homework really implies. Now conceptually, what is it? Okay, for those of you that really want to learn a deeper dive into it, let's look at this molecule here, C2H4. Here's the Lewis structure for C2H4. And in the middle, we see a double bond. And that's the bond we're going to really look at to see what the difference between a sigma bond and a pi bond is. First of all, if we look at each carbon is identical to the other carbon. How many electron domains are on each carbon is its own centralized atom. So we could look at the number of electron domains on each carbon and the shape of it and the bond angle, which we see is all the same because they're identical on each side. The left and right carbon both have 3 electron domains because that double bond in the middle only counts for 1 electron domain. Therefore, since each of them has 3 electron domains, they each will form a 120-degree bond angle, and the geometric shape will be trigonal planar. Okay? So now let's take a look at a deeper dive of what a sigma and pi bond really is. Now we know from the electric configuration of carbon, we get 1s2, 1s2, and typically it's 2s2 and 2p2 as well. But from our last electron hybridization, one of the electrons in the 2s jumps in, so we have 1 electron each in the 2s and 2p orbitals. The same thing happens on the bottom below. Now, if you were to put a circle on all 4 of those, that would indicate, in essence, a quadruple bond, which isn't the case that happens here. So what ends up happening here is because we have 3 electron domains, what hybridization must take place? Remember from the last lecture, you have 3 electron domains. That means you must have sp2 hybridization. Therefore, one of the s's and 2 of the p's come together to hybridize, which would be what I'm going to box in right here. So those 2 hybrid orbitals morph together to form 3 sp2 hybrid orbitals. So we end up getting now is sp2, sp2, sp2. There's still the 1s for the carbon, the other carbon, and then we still have a p orbital over here that is not hybridized. It's an unhybridized orbital. Okay? So the inner shell electrons don't take place in bonding because they're full. So what ends up happening now here is we have now three equal areas which can take place in bonding. Now they don't bond to themselves. If they were to bond to themselves, then there would be a triple bond between them. That's not the case. What ends up happening with this carbon molecule is, if I'm doing 120-degree bond energy, is that those three orbitals form the geometric sequence because those are all going to be a sigma bond. Now, two of each of the carbons sp2 hybridize will overlap and bond with the hydrogen, which is a 1s orbital. So the carbon and hydrogen bonds that form, the four of those that bond up here in this Lewis structure, right here, these four, these will all be equal energy because it's an overlap or a bond that takes place between a 1s hydrogen orbital with a sp2 carbon orbital. So that would be the bond energy associated with that carbon-hydrogen bonds. And there's four of them that take place. Okay, one on top right, bottom left, top left. And then there's also one of the bonds that will take place will be an actual overlapping between carbon themselves, because the two carbons will bond to each other, and that bond will be the bond that forms between an sp2 and an sp2 each of carbon. Okay, and from that we get the bond angles 120 degrees, and we can see that for both carbons we get this perfect trigonal planar shape. This is a flat molecule. It all exists on a single piece of paper, one single plane, and all the bond angles there are 120 degrees between the carbons and the hydrogens. Okay, between the carbons themselves, that'd be just 180 degrees because they're across from each other. But each of the carbons would be 120 degrees to each other, all the different bonds. Okay, now what about this pi bond? Well, now we're going to look at the unhybridized bonds. So if I turn the page here, what I'm going to do is I'm going to take that molecule now and make it flat. So I'm turning that plane of paper as best I can. I'm still going to kind of show you. But now I've got this flat disk of paper where we've got this trigonal planar shaped molecule along with the hydrogens that it's bonded to. But there's still the pz orbitals that I said on the previous page that were unhybridized. So what happens is we still have this p orbital, and because unhybridized, it's still shaped as a dumbbell, top and bottom, in which we have an electron in each of these. Okay, with arrow up and arrow down. The pi bond now is going to be a bond that takes place between unhybridized p orbitals. So the p orbitals that don't take place in the bonding will now form a bond with each other, forming what's called a pi bond. And so what will happen is there will be a bond that forms between these orbitals, which we will connect them. And you can see why now, if I just look at this basic shape, why they've given this a pi bond shape. You can see that shape that takes place. Now, it also occurs on overlap on the bottom, but you can see why on the top, why they do call this kind of like a pi shape. So what we have now is a sigma bond that occurs in the disk of the material, which is where we get the electron domains and the basic shape of the molecule. But then that double bond is going to be that second bond now that results in a top and bottom sequence surrounding that sigma bond. And because of that pi bond that forms, that's going to make this bond a lot stronger because of that second bond, and a lot shorter. As it gets stronger, it pulls the carbons in even closer together, and that's because we know back from way back in this third unit that a double bond is shorter and stronger than a single bond. And that's because there's a second bond that takes place, that overlapping in another three-dimensional space, and that increases the strength and shortness of that bond. Okay? And in a triple bond, we would have the sigma bond in the middle. We would have a pi bond at overlap in the y-axis, and then we'd also have one along the z-axis, coming out in front and behind. So in a triple bond, the sigma bond is in the middle, and then we have a pi bond on the top and along the sides. So we have now all three dimensions, x, y, and z, where the x-plane would be the sigma, and then the y and z would be the overlapping between two unhybridized p orbitals that results in two pi bonds, which again makes it even stronger than a double bond and even shorter than a double bond. So, but for the national exam, this is a type of question you might be asked. You might be asked to draw a Lewis structure. One of the questions might be as quickly as saying, how many sigma bonds and pi bonds are there? So if you look at this molecule right here, pause the lecture for a second, go ahead and tabulate it out. All right, so if I count, any single bond is a sigma bond. And then in the multiple bond, one of them is a sigma. All the other bonds are pi's. So if we count them all up, we have 1, 2, 3, 4, 5, 6. There's 6 sigma bonds, and there are 3 pi bonds. A total of 9 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 bonds, which correctly adds up. 6 of them are sigma, and 3 of them are pi. That might be all you need to do. So that's how you calculate numbers sigma and pi bonds. And I also then explained what they are and schematically kind of show you, which isn't probably necessary for this national exam, but I just wanted to get you some background information that might be more useful to understand why and what these are and why they're different. Okay? Thanks again for listening. Again, fill out the next column, which is sigma and pi bonds. All you've got to do is put down the number sigma and pi. Again, it should take you no more than about 5 minutes or so to do. Good luck.